So why don't you get going?
Yeah. So I took David's idea to heart. He said, bring young people and have young people talk. So I'm not going to give the talk. Carlos, who's working with me, is going to talk about talk about our work. But I just wanted to say a few words about how I met Joe and the influence he's had. So I met Joe. I was a PhD student at MIT, and I was not very much in my supervisor at MIT was David Benny, and I was not very much on the GFD side of things. I was doing more asymptotics. And David, at some point, I think he wanted to get rid of me for a summer, and he said, why don't you go to Woods Hole for a summer? So I went to Woods Hole. I was not in the GFD community, so everybody looked very intimidating, except for Joe. Joe was sitting on the porch, and so I started talking to him, and you have to choose somebody to work with. So I chose Joe. That was he seemed like the nicest guy, and it was just I had no idea who Joe Keller was. So we started working, and it was always a great pleasure. I learned a tremendous amount from him, and he would always I think about 3 or 4 weeks into the summer when I wasn't doing any progress, he finally wrote some equations down. We finally sat down and on a piece of A4, he sort of, I think in about 20 lines, said, this is what you need to do for the rest of the summer. He used to go 1, right, that's not 2, there's 3. All right, so I learned how to do that. I went off, I wrote, then I wrote the actual summer report. He thought my English was terrible because I had long sentences. He chopped them all up. And so taught me a lot, in fact. And all this, so my whole summer was on a sheet of A4. And then I finished my PhD at MIT, and I applied for postdocs, and Joe said, well, why don't you come and do a postdoc at Stanford? I thought that was sort of good news. The biggest difference between the summer at Woods Hole and the postdoc at Stanford is that instead of writing what we should be doing on a piece of A4, it now went down to A6. It was about a little piece of paper like this. He would open his desk, pull a tiny little piece of paper and write down what you're supposed to do for the next 2 months on a piece of paper. I don't know if that's what he thought of me, right? I didn't deserve the A4. We should go down to the A6. Maybe some of you had A3. But in any case, that was Joe. And since then, we worked on several problems together, also with Jean-Marc, and it's through Joe that I met Jean-Marc. We met many times since then, and Alice, of course, very often. So I'll leave it up to Carlos to say something about what we've been doing and how it relates to what Joe is working on at some point.
Thanks, Phil. Before I begin, I'd just like to thank the organizers. And I must say I didn't have the honor to meet Joe Keller. However, I have, until today, the privilege of learning from people who work with him directly, as you can see. And so I want to tell you a little bit about what we're doing along those lines. So this is the problem we're concerned with. We have a container of fluid, a superhydrophobic ball falling into it, which is actually heavier than the fluid, but does not sink in because of its hydrophobic property. So it's coated with a hydrophobic coating. So we want to understand how this impact and bounce off happens, right? So this brings us back to a static version of a problem, which was dealt with by Joe Keller, and it's got a very nice conclusion to it, which is a generalization of Archimedes' principle, right? So in this brief paper, Joe shows that you can apply a pressure here which corresponds to the pressure on the fluid on a ball that's sitting on the fluid surface, and at the boundary, at the contact line, the effect of surface tension is actually equals to a force that it's equal but opposite to the weight of this mass of fluid that's being displaced by the meniscus, right? Our problem resembles this, but it's sort of a dynamical version of it. So as a first approach, what we do is we assume that during impact, the fluid has a contact area, which we will then have to determine what it is. But it will change throughout the impact. The pressure on the solid during impact basically responds to the pressure on the fluid at that point, and surface tension jumps. Right? So we start by linearizing the free surface equations. We do some approximations. We assume for now that the solid is perfectly hydrophobic. That means that the contact angle is always flat. And we have to find the pressed area at each time with those conditions, right? So tangency at the contact line. So this leads to a non-local formulation of the problem in physical space. We do it in physical space because we have to decompose the domain in two parts. So there's a part that's subject to the pressure, and there's a part that's essentially a free surface, right? So why is it non-local? Because we want to reduce a problem to a 2D problem on the surface, and so we have this set derivative of the potential, which is Laplacian free in the whole volume. So this means we have to deal with a Dirichlet-Neumann operator on the free surface. And in the linearized problem, we can model that as an operator that takes phi and gives us phi set for the Laplace problem. And we do this design of a domain of integration, and then we use Green's identities and Green's functions to derive an expression for this singular integral operator, right? And it's sort of an unusual expression for some people because it's very singular, but we show that this actually works, that this operator is well defined and converges and everything. It's somewhat difficult to deal with it numerically, but we found a way to do it. We have to use the fact that the kernel is radially symmetric. We're working in a problem which is radially symmetric as well, but symmetries are around different axes, so we have to use different meshes. We also have to find a way to carefully interpolate this integration integral operator. So you have to interpolate the function and not the kernel, for example, which is not so simple in a 2D domain, but we get through it, and we add equations for the solid, and with this we have a closed system for each fixed contact area. So if we assume we have a given contact area, we can solve the system and find the shape of the interface. However, that shape might not fit the tangency condition at the boundary of the contact area. So if we choose a contact area that's too small, we might get something like this, where there's a subtle but a noticeable difference between the free surface and the droplet, or the sphere. If we choose too big a contact area, we get something like this, which is not realistic. And so we have to find this right area, right? So we iterate on the contact area, and we obtain these simulations. So we now let the solid ball hit the free surface. It sinks in, and at each time we're choosing the optimal contact area in the sense that there's no superposition between the two masses, and the tangency is as close to 180 degrees at the contact line, right? So we were fortunate enough to find experimental results. So a team, Lee and Kim in 2008 published this paper where they study this phenomenon, where they drop a solid hydrophobic sphere onto a fluid bath, and the gray circle is actually their tracking of this sphere, and the black circle is our simulation, right? So we essentially just take the same initial parameters and run the simulation, right? So there's no wave for the gray circle because they only track this sphere, right? So this the simulation you just saw corresponds to the black dots. Those are the positions of the center of the gray circle. And Lee and Kim actually developed a model which they show it predicts the initial and final stages of impact, but not the middle part. And sorry, like this. Okay, sorry. So we use our model, And we produce, okay, so the crosses here correspond to the circles here. The black curve is the tracking of the center according to our model. This is the south pole of the droplet, or the sphere. And this is the free surface just underneath the south pole. So in a way, we're at least improving the predictions here. Okay, once we have this model, we wanted to apply it to a different problem, which is related, which is bouncing droplets. So maybe some of you have heard of this, but if you haven't, it's more likely that you've heard of the coalescence cascade, which is this phenomenon that happens when you release a tiny droplet of the same fluid as an underlying bath, and it takes some time for it to start to coalesce with the underlying bath. Right? This is because there is an air layer that needs to be drained before coalescence can commence. Right? And so if you combine this with the Faraday instability, which happens when you shake a bath with a given frequency and above certain amplitude, your free surface goes unstable to field surface waves. So if you do the releasing of a droplet on a shaking bath within a certain parameter regime, you can actually inhibit coalescence permanently. So you can get this periodically bouncing droplet, right? So this is a curious object. It's essentially an association of a droplet and the wave that's formed on the free surface by its history of previous bounces, right? And so for small droplets, droplet deformation is not as big as shown here. So this is a big droplet, right? But this one doesn't deform so much. So we said we might just treat the droplet as a solid ball and try to use our model, right? So we did that, and this is what the simulations look like, right? So the black dotted line is where the free surface level of reference is, because this is being driven. Then the blue line is the wave on the surface, and the solid sphere, which represents the droplets, just moving and impacting according to this model. Right. So this all looks very nice, but how does it compare to the experiments? This is a very interesting picture from the experimentalists. The shaded regions indicate moments where the droplet starts to touch down and when it lifts off. Okay, so this is for the same droplet, and shaking amplitude increases here, and modes of bouncing go changing as you increase the shaking amplitude, and time increases here as measured by the phase of the shaking, right? So every, well, here at the bottom everything is flying, so each vertical traverse corresponds to one driving amplitude. So you start here, you move up in time, and you reach this first shaded region, you touch down, you stay in contact until you reach the blue one, right? And then you fly again. Okay, so the same droplet is driven at different amplitudes, and then you have flight, contact, flight again, and then contact here, and then flight again here, right? So we ran the same simulations that correspond to these parameters, and we get this prediction, right? So we're able to predict with this model, which is parameter free, at least for the impact. The only thing that we actually tune is viscosity in the fluid to get the right Faraday threshold. But with this model, we can predict at least the phase of the shaking with qualitative accuracy. And we can also produce a prediction for the wave field, which is actually measured in the laboratory. And this is how it compares. So the gray thick line back is lab results, and the black line is our simulations. Right. Okay. And this is how it looks when you put it all in 3D. Right. So we generate the wave, and the system's being driven. Right. So. Thanks
very much for sticking to time. So we've got time for a couple of questions.
Can you comment on this wave theory and its applicability to quantum?
Yeah. Well, I left that out because it gets too interesting, right? But I did cheat putting extra slides here. So if you keep driving the system, a lateral instability sets in, and basically this bouncing droplet becomes a walker. So it starts moving horizontally. And then you can do all kinds of fun stuff, right? Like the interaction between two weight fields of two walkers gives rise to an analog of an exclusion principle. And also you can make it interact with submerged topography. And so you have, you can reproduce single and double slits experiments, right? So this is the next thing we want to do. We want to put this model to walk. We're working on it. Thanks.
Any other questions?
So maybe I'll make a comment, a more philosophical comment on that. So there's a lot of quantum mechanical analogies in this problem, and whether it can lead to, let's say, a more deterministic version of quantum mechanics, that's up to everybody's personal taste. But I think what it does show is how a classical system can behave in a strange way like quantum mechanics.
Yeah.
So it might help you to filter what is truly weird about quantum mechanics and what is not so weird. What could be in fact explained classically by some other means.
And on that note, we'll leave that to a later discussion. So if we could thank Carlos and Paul.
Yeah. So